Now moving onwards, we are going to start the topic of boundary layer similarity, the normalized boundary layer equations. So over here it says that the boundary layer equations are normalized by defining some dimensionless variables. We define x star as the ratio of x to the total length. Similarly, we define y star as y over L. We define u star as u over the free stream velocity. We may write it as v or u infinity. And v star as v upon capital V. Kindly note that small v refers to the component in y direction, whereas capital V refers to u infinity or the free stream velocity. And then we define p star as p over rho v square, because we know that half rho v square is pressure, so therefore rho v square would have the same units as that of pressure. All those in fact are dimensionless. X star, y star, u star, v star, p star and t star, they all are dimensionless quantities. And this t star shouldn't be new for you, because we have discussed it, this ratio, while we were discussing the thermal boundary layer, where this ratio would approximately be equal to 1 if we are near the end of the boundary layer. Now if we substitute all those in these equations, in these three equations, which are the conservation of mass, momentum and energy equations, which we have just derived a little earlier, so we will get these. See, let me show you let me show you the working for a couple of equations. I will show you the working for continuity equation and momentum equation, and on the same lines you can then derive this form of energy equation starting from here. So let's start with the first one. Dava u by dava x plus dava v by dava y is 0. Now if in this equation we put all those parameters, all those dimensionless parameters, so in place of u we will write in u star times v, and in place of x we will write x star times L, Similarly dava v, so v would be v star times v, over dava y, and y is y star times L, So now v, since it is constant quantity, would be taken, it is u infinity in fact, would be taken out of the differential sign, and similarly L, which is the total length, which is constant, would be taken out of the differential sign as well. And over here v and L would be taken out of the differential sign. So we would be left with dava u by dava u star over dava x star over here, and in the second term we will be left with dava v star over dava y star as is written over here. Now if we take v by L common from both these equations, so 0 upon v by L would become 0, and we will be left with dava u star by dava x star plus dava v star over dava y star as 0. This is the equation that was written over here. So starting from the regular continuity equation, we can end up writing the continuity equation in those dimensionless variables u star, x star, v star and y star. Now I am going to show you the working for the second equation, means the momentum equation. Now this is the momentum equation, right? Now we can write this u as u star times v, and then it says dava u by dava x, so it would be dava of u means u star times v over dava x means x star times L plus v would be written as v star times capital V, and u would be written as u star times v over y, so y would be written as y star times L, So therefore in place of y we have written y star times L. On the right hand side it is mu over rho times second derivative of u will be written as u star times v, and similarly y over here will be written as y star times L, and p will be written as p star times rho v square, p star times rho v square, and x as x star times L. Now from the first term v by L will be taken out of the differential sign. So we have u star times v written previously, and then we will multiply it by v by L, and it would be dava of u star over dava of x star. In the second term we already have v star times v, capital V, and then v would be taken out of the numerator, out of the differential sign, and similarly L will be taken out of the differential sign in the denominator. So it would be v by L over here, and therefore we would have dava of u star by dava of y star, and we have mu over rho over here, and v would be taken out of the differential sign, and similarly L square will be taken out of the differential sign because it is dava of this thing squared. So we would have dava square of u star over dava of y star squared minus 1 upon density. So over here only p star would be kept inside the differential sign, and rho v square will be taken out, and from the denominator L will be taken out of the differential sign. So it would be d of p star over d of x star. Now this v and v would become v square, so it would be v square by L. This will also become v square, so this will be written as v square by L. On the right hand side it would be mu over rho times v over L square times this thing, and means the first term on the right hand side remains the same, whereas in the second term the density will get cancelled out, so it would be v square by L and dp star over dx star. Now if we divide throughout by v square by L, so we would have u star times dava of u star by dava of x star as the first term on the right hand side. The second term on the right hand side would be v star times, since we are dividing throughout by v square by L, so this will vanish, and we will be having dava of u star over dava of y star as the second term on the left hand side. On the right hand side again v by L square will vanish, and we will be left with mu upon rho times it will not vanish. Kindly note that since we are dividing by v square by L, so we would have a v in the denominator and L in the denominator as well, right? Because v upon v square will give us v in the denominator, and L square upon L will give us L in the denominator, times second derivative of u star with y star minus, since we are dividing by v square by L, so this term would vanish, and we will be left with dp star by dx star. Now the left hand side would remain unchanged, so the left hand side remains unchanged. Only on the right hand side we see that this is rho v L over mu, and this rho v L over mu is nothing but the Reynolds number, so we would have Reynolds number in the denominator. The rest of the things remain unchanged. So this is how we can get, this is the same form which is written over here. This is the same form which is written over here, which is the momentum equation in terms of the normalized dimensionless variables starting from this momentum equation. So I have shown two. You can do the third one on your own using the same method. These are the this is section 6.5 of our book, and this is table 6-1, which shows that there are conservation equations written in the form of the dimensionless numbers. Instead of u and v and t, we have got t star and u star and x star and y star. So these are the two equations that are written over here, and I have shown both of I've shown you the first one with the velocity one, and you can do the third one, which is the energy equation, by yourself. We are not discussing the concentration equation because we have not considered the concentration boundary layer till yet. We would inshallah be discussing it when we will learn the topic of mass transfer. So this is 6.35 and this is 6.36. Kindly note that both these equations will come into discussion in a bit. Will come into frequent discussion in a bit. Now over here we are talking about the boundary layer similarity and the normalized boundary layer equations, and you would have learned about similarity during your fluid mechanics course. Right, so what was the, if you recall, what was the use of similarity over there? The use of similarity or similitude was that we could apply the results from one machine or one prototype onto the actual large size machine. Right, so that was the use of similarity study that you have already gone over during your fluid mechanics course. That the and if you recall, you would have gone over Buckingham Pi theorem and all that, right? So so over here similarity has got the same meaning, and the normalized boundary equations would also be used for the same purpose. And over here you can see, let's first of all go over those things. But first kindly note that those results can only be applied to geometrically similar objects. The object should be geometrically similar. So over here it says that as long as the similarity parameters and dimensionless boundary conditions are the same for the two set of conditions. Two set of conditions means for the prototype and the actual large size machine, or any other two set of conditions. For example, over here we see that the two set of conditions are that the objects are geometrically similar, however they are not exactly the same. Similar is something else and exactly same is something else. So they are similar objects, but they are of course not exactly the same. And if it is such that that on one the water is flowing over the surface, and in the second case the air is flowing over the surface with of course different velocities, but the combination is such. Combination means the combination of the geometry and the flow is such that the Reynolds number are the same, and then the coefficient of friction would also become the same, right? So this is how we make use of the similarity studies, that we can apply the results obtained from one object onto another object provided they are geometrically similar. So it's not new thing for you. You have already gone over the similar kind of study under fluid mechanics course, in the fluid mechanics course. So over here, that if the two objects are if there are two set of conditions, etc., etc., the solution of the differential equation of table 6.1 for the non-dimensional velocity, temperature and species concentration will be identical. So what is being said over here is a very important thing, and it says that if there are two objects which are geometrically similar, and they have the same sets of condition, so then the solution of the differential equation for the table 6.1 would be the same. Now what is meant by that? What is meant by the solution of differential equation? See, solution of differential equation would be that quantity of interest. For example, if we have the differential equation, let's say dou t by dou x, so the solution of this equation would be t as a function of x, would be temperature distribution. We would be having an equation in which t would be written as a function of x. So this is what is meant by the solution of the differential equation. So now we are going to discuss this particular section, which is 6.5.2 of our book, the title of which is functional form of the solutions. So it's not at all difficult as it looks. It's a very easy kind of discussion. So it says that solution to equation 635 will be of the function form this. Now what is 635? If you go back, so this is 635, and this is the one that we had derived. So solution to this equation. Now solution to this equation would mean u as a function of the rest of the parameters, u star as a function of the rest of the parameters. So whenever we try to find out the solution of any differential equation, we integrate it, and we then put the boundary conditions. If you recall, we had done the same thing while we were on chapter number 3, where we had an equation, and then we had integrated it twice to get the temperature distribution. T was C1x plus C2 in the case of Cartesian coordinate system, and then we had applied the two boundary conditions. And then when we came on to the cylindrical coordinate system, we had, if I remember correctly, it was T as C1 log of R plus C2, and then we had then applied the, so where did we get that T as C1 log of R plus C2? We had integrated an equation twice. So therefore first C1 came in, and then C2 came in, and then we had two sets of boundary conditions which we had then applied to find out the values of C1 and C2. So over here, if this is the differential equation and we want to find out its solution, so we would be integrating it, and that integral would give us the solution in terms of x star, will give us the solution of u star in terms of, or as a function of, x star, y star, dp by dx. Whether we consider dp by dx or not, it does not matter, because we had seen that dp by dx in x direction does not change, so it remains 0, and in terms of Reynolds number. So now going back, so u star, the solution to that equation would give us u star as a function of, or in terms of, x star, y star, Reynolds number, and dp by dx. Again, you consider dp by dx or not, it does not matter. Also, the shear stress can be written as mu du by dy or dou u by dou y, and then we can put that u as u star times v, as u star times v. So v would be taken out, and it would be dou of u star, and then again in the denominator it has dou y. So y can be written as y star times L, and since L is constant, so it would be taken out of the differential sign. So we would have dou of y square left. Now similarly, the friction coefficient can be written as Ts over half rho v square, because Ts is Cf times half rho v square. This is what we had discussed in the very initial slides of this chapter. So tau s, not Ts but rather tau s, shear stress. So tau s can be written as mu v over L times dou y of u star over dou of y star. So we have put that thing over here in the denominator, and in the numerator, and then in the denominator we have half rho v square, right? So now this mu, so this 2, first of all this 2 will come into the numerator, so it has come into the numerator over here. This mu will remain mu. This v upon v square, will give us a v in the denominator, so we would have v in the denominator. We would have a rho along with v, so we have a rho along with v in the denominator, and this L lies in the denominator, so this L will come into the denominator, times dou u square, dou u star by dou y star, so we would have dou u star by dou y star. Now again this rho v L over mu, is in fact the Reynolds number, so it would be Reynolds number in the denominator. The rest of the things will remain the same, 2 remains 2, and dou u star by dou y star has been written as it appears in the previous step. Also from this very first step, dou u star by dou y star would then be a function of x star and not y star, because we are differentiating it with respect to y star, so therefore its solution will not have y star with it, and then Reynolds number will be there. Again, whether we consider dp by dx, it does not matter. So hence, for a prescribed geometry CF, so what we are going to do over here is that we are going to write this thing in here, in place of dava u star by dava y star. And what is this thing? It is CF. So therefore CF would be 2 over Reynolds number. CF would be 2 over Reynolds number times dava u star by dava y star, and dava u star by dava y star is a function of x and Reynolds number. Is a function of x star and Reynolds number. Again, we are not interested in dp by dx because it would not exist. So hence, for a prescribed geometry, CF must be a function of x star and Reynolds number, right? So these are very big equations, but they are not that difficult to understand. Now moving forward, over here on the previous page we were talking about velocity. Now we are talking about temperature. Means now we are talking about, in the previous slide we were talking about hydrodynamic boundary layer, the velocity boundary layer. Now we would be talking about the heat transfer, means we would be talking about temperature or thermal boundary layer. And it says solution to equation 636. Now if we go back and take a look at equation 636, this is equation 636. So what would its solution be of the form? What form will its solution have? Its solution will give us T star as a function of x star, as a function of y star, and as a function of Reynolds number and Prandtl number, right? Its solution will give us T star as a function of x star, y star, Reynolds number and Prandtl number. So this is what we will see written over here, that the solution to that equation 636 will be of this form, that we will have T star as a function of x star, y star, Reynolds number and Prandtl number. Also H is this thing, right? And if you recall, where did we get this expression from? In fact, we have discussed this expression twice. Once while we were on chapter number 1, and then again we had discussed it at the beginning of this chapter. So what does it say? It says that the heat transferred via conduction from the surface to the first layer would be via pure conduction, so it would be minus Ka dava T by dava y, and then it will be transferred to the subsequent layers via convection, so that minus Ka dava T by dava y at y is equal to 0, means at the interface of the surface and the fluid, would then be equal to Ha delta T. So area will get cancelled out, so therefore H would be minus K times dava T by dava y over Ts minus T infinity. Now if we do the same thing over here, means if we put T as in terms of T star, right? So what is the expression over there while we were discussing the normalized boundary conditions? This was the thing, right? So T star was T minus Ts over T infinity minus Ts. So what would T be? T would be T star times T infinity minus Ts plus Ts. T would be T star times T infinity minus Ts plus Ts. So T would be T star times T infinity minus Ts, so and plus Ts. So plus Ts is a particular term, is a separate term. So the differential of that particular term would be 0 because it is Ts, and Ts is in fact constant quantity. So therefore its differential would become 0. And while differentiating T star times T infinity minus Ts, so T infinity minus Ts is the coefficient of T star, so it will come out of the differential sign and we will be left with dava of T star, right? If you can do it, I mean you should do it by writing it on the paper, and you will see that it is not difficult at all. Over dava y, so we will write y as y star times L. So y star would remain with dava sign and L would be taken out of the differential sign. Now we have kf, so we have kf written over here, and we have ts minus t infinity in the denominator. So we have ts minus t infinity written in the denominator. So if we take this minus sign inside over here, so it would become ts minus t infinity, and therefore that ts minus t infinity will get cancelled out, and we will be left with kf by L, where kf is the conductivity, thermal conductivity of the fluid, times dava T star over dava Y star. Now Nusselt number, which is HL over K, so H is this thing. So if we take this L in here, and if we multiply it by H, and if we take this K into the denominator of the left hand side, so on the left hand side we would have HL over K, which is nothing but the Nusselt number. And what we would have on the right hand side, dava T star by dava Y star. So we would have on the right hand side dava T star by dava Y star. Hence for a prescribed geometry Nusselt number, so dava T star by dava Y star, right? So what would be dava T star by dava Y star? Dava T star by dava Y star will not have Y star in the functional form. So everything would be there except Y star. So we would have X star, Reynolds number, and Prandtl number. It means that Nusselt number would be a function of X star and Reynolds number and Prandtl number for a prescribed geometry. If we talk about average heat transfer coefficient, so as discussed previously in this chapter, there are two heat transfer coefficients. One is what we call the local heat transfer, convective heat transfer coefficient. The other one is what we call average convection heat transfer coefficient, where average is denoted by H bar and the local is denoted by Hx. And as we have seen previously, that H bar is 1 over a integral of HdA, or H bar is 1 over L integral of Hx dx. So if you are talking about the average heat transfer coefficient, then even X star would not be there, because we have averaged out all the things. We would have integrated the things over the entire length. So X star would not be there, of course, for the very obvious reason, and therefore average Nusselt number means Nu bar, Nusselt number average, would be a function of Reynolds number and Prandtl number only, and it will not be a function of X or X star. This is what is meant by functional form of the solutions. So over here you can see that we have what we have. First of all, see the headings: fluid flow and heat transfer, right? So this is what we saw a couple of slides earlier, and this is what we saw on the last slide. Again, having dp by dx or not having dp by dx will not make any difference. So U star would be a function of X star, Y star, and Reynolds number, whereas in case of temperature, it would be X star, Y star, and Reynolds number along with Prandtl number. So it would be X star, Y star, and Reynolds number along with Prandtl number. And this is what we saw in the case of coefficient of friction, and we had seen that coefficient of friction was 2 over Reynolds number and some function of X star and Reynolds number, right? I can go back over there. This is the expression that is written over there. Which is equation 6-46 in the book, 645 and 646. However, when we come on to the temperature, so we would be having Nusselt number. See the comparison: fluid flow versus heat transfer. Fluid flow means velocity, heat transfer means temperature. Over here we had the coefficient of friction, over here we have got the Nusselt number. So we have written Nusselt number in this form, and then the average Nusselt number was a function of X star, Reynolds number, and Prandtl number, whereas the average Nusselt number, this was local, 649 was the local, and the average Nusselt number did not have X or X star in it, so it was a function of Reynolds number and Prandtl number only. Now moving on to the end of the chapter, we are going to discuss boundary layer analogies. We had derived those equations 635 and 636, and we had seen them in that particular table as well. So now if in this momentum and if in this energy equation, if dp by dx is 0 and if Prandtl number is 1, now Prandtl number may be 1, it would be 1 for gases, right? So, such as for air it would be approximately 1, to be very exact it is near 0.7. But if the Prandtl number is 1, then what will happen is that uh, the Prandtl number will not exist in equation 6-36. So in this equation 6-36 will then be written as 1 over Reynolds number times second derivative of t with y. Second derivative of t with y. And if dp by dx is 0, then of course 6-35 will be written without dp by dx. So if we compare these two equations, we will see that they both have the same form. Again, they are not exactly similar, but they have a lot in common. They are not exactly same, but they are similar, right? So they are having the same form. And what is that same form? See over here in these two equations, it is u star, we have u star, we have derivative of u star with x, so we have derivative of temperature with x. Again we have a derivative of velocity with y, so we have derivative of temperature with y. On the right hand side we have 1 over Reynolds number, so we have 1 over Reynolds number. And we have second derivative of velocity with y star, so we have second derivative of temperature with y star. So everything is the same, everything is similar except velocity and temperature, right? So that is why one is talking about the velocity or momentum, and the second one is talking about temperature or thermal boundary layer. So hence the functional forms of the solutions for u star and t star must be equivalent. Of course, in here we would have u star as a function of x star, y star and Reynolds number, and in the second one we would have t star as a function of x star, y star and Reynolds number. So therefore the functional forms would be equivalent, right? And the functions u star and t star would then be identical. The only difference would be that one equation would be in u star and the other equation would be in t star. That would be the only difference. And therefore the first differential would also be the same. If the equations are similar, it means that the first derivatives would be the same, right? So then now in the continuing the same discussion, it says using equation 648 and 645. See what are 648 and 645. We do not need to refer back. You can recall what we have just explained on the previous pages. Nusselt number was HL over K, and Nusselt number was in fact written as dava T star by dava Y star, right? So we had written the Nusselt number as dava T star over dava Y star, and then the same thing has been written over here. And from now on, if since we have seen that u star and t star would have the same functional form and their functions would be identical, and if the functions are identical, then of course the first derivative would be the same, and therefore dava t by dava y star can be written as dava u star over dava y star. So that is why we had written on the last line of the previous slide that the derivatives of the two would be identical if the functions are identical, and when the functions would be identical, if they have got the same form of the solution, if u star and t star have got the same form of solution. And then dava u star by dava y star is Cf times Reynolds number by 2. This is what we had seen in the velocity or hydrodynamic boundary layer portion. I can show you that dava u star over dava y star is Cf times half Reynolds number. Yes. See, dava u star by dava y star is Cf times Reynolds number by 2. So this thing is equal to Cf. So Cf will be multiplied with the Reynolds number, and then 2 will go into the denominator of the left hand side. So coming back so this is what we can write over here. Now after discussing so many dimensionless numbers, Reynolds, we have discussed Reynolds number, we have discussed Prandtl number, we have discussed Nusselt number. Now we are going to discuss one more, or introduce one more dimensionless number, which is called Stanton number. This Stanton number is a ratio of Nusselt to the product of Reynolds and Prandtl. So if you write Nusselt number as HL over K, Reynolds as rho VL over mu, and Prandtl number as rho Cp upon K, then we will get this expression, right? So it's not difficult to get this expression if we write the original expression of Nusselt number, Reynolds number, and Prandtl number. Now Nusselt number, which is Stanton number, which is a ratio of Nusselt to Reynolds Prandtl as per this definition, would be equal to Cf by 2 if Prandtl number is equal to 1. Would be equal to Cf by 2 if Prandtl number is equal to 1. How? From here. From here. See, if we bring this Reynolds number in the denominator of Nusselt number, so it would be Nusselt upon Reynolds, and if Prandtl number is 1, so that would be equal to Cf by 2. That would be equal to Cf by 2. Right, so this expression, that is Stanton number, is ratio of Nusselt over Reynolds Prandtl, which reduces to Cf by 2 if Prandtl number is 1. That expression is called a Reynolds analogy. But again, there are two statements behind this Reynolds energy. First one is that dp by dx is 0, and majorly Prandtl number is 1. However, if Prandtl number is not equal to 1, it has been found that this same expression Cf by 2 may be written as Stanton times Prandtl number raised to the power 2 by 3. And this expression holds good for a wide range of Prandtl number ranging from 0.6 to 60. So if Prandtl number is not 1, then this expression would hold good, and this particular expression is called modified Reynolds analogy or Chilton-Colburn analogy.